Why are almost all the airplanes in the world white? Is it a simple aesthetic matter, or is there a much deeper reason that almost no one knows? The answer is not obvious. What at first glance seems like a minor detail hides decisions that go far beyond the visual. If we observe any airport from a distance, the scene is almost uniform. Dozens of airplanes lined up, each with its own particular design, but all sharing something in common: the white fuselage shining under the sun. It does not matter whether they are short-haul airplanes, intercontinental giants, cargo aircraft, or private jets, they all share that same predominant white. And yet, very few people know why. Some believe that dirt is less noticeable that way. Others think it is a tradition that became established over time, and, for many, it is simply an aesthetic matter. But none of those explanations is enough to understand the true depth of this decision. On an airplane, white does not serve a decorative function, but rather acts as a tool, a protection, and a critical layer within the system that keeps an aircraft safe, efficient, and operational. And although today we see it everywhere, it was not always like that. In fact, it became the dominant option because it solved problems that were not evident at first glance, but that could affect everything from the internal temperature to structural maintenance. To understand why white dominates the skies, one must look at what really happens when an airplane spends hours under the sun, and why color can be the first line of defense against heat and radiation. Under those conditions, an airplane is not simply parked without more. It is absorbing an enormous amount of solar radiation that heats its fuselage, its interior, and many of the systems located beneath the metallic or composite skin of the aircraft. The external temperature can rise quickly, and the interior can become a true thermal chamber if it is not properly controlled. Therefore, to answer the question of why airplanes are white, one must first understand how the sun physically affects an aircraft, even when it remains completely motionless on the ground. For entire hours, solar radiation strikes directly on the surface of the airplane, and, in airports with warm climates, an exposed fuselage can reach high temperatures that place stress on materials, sealants, joints, electronic equipment, and auxiliary systems. In that process, the structure absorbs that energy, and the darker the color of the surface, the greater the heat it retains, which not only affects the comfort of passengers once on board, but also impacts the efficiency of the air conditioning systems and the temperature that numerous internal components must withstand. It is at this point that the painting of the fuselage stops being a cosmetic detail and becomes a true thermal control tool. White is the color that best reflects solar radiation. It does not completely eliminate heat, but it significantly reduces the amount of energy that the fuselage absorbs. In practice, an airplane painted white can remain several degrees cooler than one with dark colors, which reduces thermal stress on its materials and systems. In an environment where every degree counts, this difference is crucial, since the electronic components of the avionics, the auxiliary batteries, the cables, and the composite surfaces suffer less when the fuselage does not overheat, which helps maintain the stability of the aircraft before starting the engines and reduces the effort that ground cooling equipment must make. But it only takes changing a single variable for that entire balance to disappear. If airplanes were dark, the scenario would be completely different. Since internal temperatures would rise rapidly, the energy consumption required to keep the interior in safe conditions would be much higher, and composite materials could deteriorate sooner due to thermal accumulation. That is where dark paint begins to work against the aircraft by absorbing more radiation and increasing the temperature of the fuselage, which forces the climate control systems to operate longer and at greater power. As the fuselage heats up, thermal expansion also increases, affecting joints, panels, and coatings. In aviation, keeping an aircraft cool is not a whim, it is efficiency. The less an aircraft overheats, the less fuel is consumed to stabilize its interior temperature, the less stress its materials endure, and the less preventive maintenance is required. White, therefore, is not simply a color, but a choice that optimizes the lifespan of the fuselage, reduces energy consumption, and enhances the overall performance of the aircraft. But the effect of white is not limited only to heat control, since by covering the fuselage it also turns the airplane into a surface where problems can appear before they worsen. And that opens a new question. If white helps keep temperature under control, how can it also help detect damage, leaks, and critical signs in the structure of the airplane? When a technician approaches an aircraft on the ramp, they do not observe just a motionless machine, but rather examine a surface that reveals what is happening beneath it, where each panel, each joint, and each rivet can betray changes, marks, or anomalies that would go unnoticed under other conditions. And it is in that silent inspection where white plays a key role because it makes visible what would otherwise be hidden at first glance. Thus, a minimal oil leak that on a dark fuselage could go unnoticed for hours becomes a clear signal on a white surface. The same occurs with hydraulic fluids, with fuel, or even with abnormal condensation patterns that reveal thermal problems or internal leaks. In aviation, where a small sign can anticipate a major failure, that early visibility becomes a decisive operational advantage. But leaks are not the only thing that white allows to be identified. The surface of the airplane is constantly exposed to impacts from small objects on the ramp, to particles during flight, and even to birds. Impacts that can leave subtle signs such as dents, scratches, or small irregular marks. On a light-colored fuselage, these differences in texture are perceived much more easily because the light generates more defined shadows over any irregularity and makes defects stand out immediately. That same contrast also facilitates the detection of early corrosion, which usually begins as a slight change in tone or as a tiny spot where the paint starts to lift, signs that are much easier to identify when the background does not visually compete with the problem. The same occurs with surface cracks, because although these initial fractures may be almost invisible, the contrast created by a dark line or a shadow on a light panel makes it easier for an inspector to identify them, even from several meters away. In modern aircraft, where part of the fuselage is composed of materials such as carbon fiber, delamination and slight deformations can generate anomalous waves or reflections that are more noticeable on light surfaces. In those cases, these visual signals can make the difference between a minor problem and a major intervention that prevents an incident. All of this becomes evident in real maintenance situations. Let us imagine an everyday scene on the ramp. The airplane has just landed, and a technician walks around the fuselage, flashlight in hand, following a routine he has repeated hundreds of times. At first glance, everything seems normal, but a small dark stain on the lower area of the fuselage catches his attention and makes him stop to examine it more carefully, at which point he discovers that it comes from a valve that has begun to leak hydraulic fluid. Thanks to the contrast of the white, the anomaly stands out as an early warning sign, allowing the problem to be resolved before it turns into a serious failure. This happens every day at airports around the world, where color contributes to safety as much as any specialized instrument. Thus, white is not only a shield against heat, it is also a visual ally for maintenance. But this chromatic choice has an additional effect that many are unaware of. The question then is clear. If white facilitates safety and inspections, how does it also influence the weight of the airplane, its maintenance, and the economics of each flight? In aviation, nothing is added without consequences because every decision, even those that seem superficial, ultimately affects the performance of the aircraft, and color is no exception. In an airplane, any increase in weight, however small, translates into greater fuel consumption throughout its operational life, and the paint, although it may seem insignificant, accompanies the airplane on every flight for thousands of hours, year after year. For that reason, an airplane is not painted like a car, since its process involves several layers, from primer and sealants to the base paint, and in some cases, a protective coating. By covering such an extensive surface, those accumulated grams end up becoming dozens or even hundreds of additional kilograms. In wide-body aircraft, that difference can even condition demanding operations, such as long-haul flights or takeoffs with tight weight margins, especially in warm climates. Hence, a simpler paint scheme and a color that is efficient in terms of coverage are not merely an aesthetic choice, but also an economic decision. This is where white stands out again, because white paint provides uniform coverage with fewer layers, and that implies less accumulated thickness. In contrast, dark or very intense colors require more layers to appear homogeneous, especially on metallic or composite surfaces, and some shades, such as black or bright red, may require several additional applications to avoid visible irregularities. All that extra material increases weight and, with it, operating costs. So for an airline, a very colorful design or a special livery not only costs more money to paint, it also results in greater fuel consumption throughout the entire service life of the airplane. Repainting an airplane is not a minor process either, since it involves a very high economic cost in each intervention and can leave the aircraft out of service for several days, which translates into additional operational losses. For all these reasons, white is not cheaper by coincidence. It is a color that requires fewer layers, weighs less, withstands the passage of time better, and remains stable with fewer interventions. When an airline opts for white, it is not choosing only a visual finish, it is optimizing fuel, maintenance, operating costs, and the service life of the fuselage. White is, quite simply, one of the most efficient decisions that can be made. But weight and costs are not the only reason why this color dominates the skies, since white also acts as a protective layer against radiation and against material wear, especially in modern aircraft built with heat-sensitive composites. The question is evident. If white helps save weight and money, how can it also protect the airplane from the sun, from radiation, and from the aging of its materials? Beyond flight hours and pressurization cycles, an airplane spends most of its life exposed to the environment. Day after day, the fuselage receives solar radiation, humidity, airborne particles, and constant temperature changes. It is a slow, continuous, and silent process that gradually degrades materials, sealants, and coatings, even when the aircraft is not in flight. And to understand how that wear acts, one must keep in mind that the fuselage of an airplane is not a uniform block. It is composed of metal panels, joints, adhesives, rivets, fairings, and parts made of composite materials that react differently to environmental wear. The paint that covers this entire assembly acts as the first line of defense against erosion and aging, because day after day the surface of the airplane receives the constant impact of rain, humidity, dust, sand in desert regions, or salt in coastal areas. In that context, white helps the degradation to be more uniform and predictable, which facilitates the detection of anomalies and reduces the need for premature interventions. To this environmental wear is added a less visible but equally decisive factor: ultraviolet radiation, one of the most important elements in the aging of aeronautical materials. In this case, the problem is not the increase in temperature, but photodegradation, radiation that breaks chemical bonds, weakens coatings, and deteriorates composites over time. Dark colors absorb much of this radiation, which accelerates wear and causes microscopic changes in sealants, varnishes, and protective layers. White, by better reflecting this type of radiation, significantly reduces the energy that materials must withstand and therefore slows their chemical aging. That same degradation process manifests itself over time in the paints and varnishes themselves. Vibrant colors lose intensity, wear unevenly, and show visible fading that forces repainting sooner than expected. Dark tones can develop surface cracks or areas where the varnish becomes dull. These irregularities not only affect aesthetics, but also the protection of the fuselage, since they expose inner layers to moisture or radiation. In contrast, white ages in a more homogeneous and stable way, which reduces the frequency of repainting and, with it, the wear associated with the very process of removing old layers and applying new ones. But aging is not the only challenge an airplane faces. Even with this protection and with a fuselage that ages more uniformly, incidents can occur. An unexpected impact on the ramp, a tight maneuver, or an error in ground operations can put this entire system to the test. And this leads us to the next question. If white helps preserve the fuselage for years, what happens when something still goes wrong and a ground incident puts all this protection to the test? The answer is not in the material, but in what is seen. On the ground, an airplane is never alone. Vehicles, equipment, operators, and other aircraft constantly move around it in an environment where visual precision is key. In that dynamic context, the visibility of the aircraft becomes a decisive factor in preventing a minor issue from quickly escalating. On airport ramps, movement never stops. Fuel trucks, loading equipment, mobile stairs, tugs, and other airplanes share the same space in a network that depends as much on coordination as on visual perception. A white airplane stands out more clearly in virtually any lighting condition, in full sun at sunset, under artificial lighting, or even on cloudy days or with light fog. That natural contrast reduces the likelihood of minor contacts and collisions which, without being catastrophic, can cause damage to the fuselage or to critical equipment, generating delays and unnecessary risks. A typical example occurs during towing operations. When an airplane is moved to or from the runway, operators must constantly monitor that there are no obstacles along the path. A light-colored fuselage allows them to see more quickly if any vehicle is approaching too closely or if a platform is encroaching on the safety zone. The same happens during parking maneuvers, especially in congested airports or during nighttime operations. Under those conditions, white surfaces reflect runway and ramp lighting better, facilitating the work of personnel both on the ground and from the cockpit. This advantage is not limited only to ground operations. Visibility also plays a role in flight. Although electronic systems are the primary tool for avoiding conflicts between aircraft, visual identification remains a complementary element. A white airplane stands out better against a background of clouds or blue sky, which helps in visual flight operations, approaches, or emergency maneuvers. It is not a decisive factor, but it is an added benefit that contributes to the set of measures that make aviation one of the safest modes of transportation in the world. The clarity of the fuselage also plays a relevant role after certain incidents. For example, if an airplane suffers a minor impact with ground equipment, the mark becomes immediately visible on a white surface, allowing the damage to be documented instantly and preventing it from going unreported. In the same way, during a nighttime operation, emergency lighting or the headlights of assistance vehicles reflect better on light surfaces, helping teams position themselves and act quickly without margin for error. All this combination of factors makes the color white contribute to operational safety more than many imagine. It reduces risks on the ground, improves the identification of damage, facilitates critical maneuvers, and provides clarity in moments when decisions must be quick and precise. It is not an isolated element, but a silent piece within the framework of procedures that seek to keep every operation under control. And behind all this, behind every inspection, every ramp maneuver, and every decision made in a matter of seconds, there are people who depend on this visibility and clarity to do their work flawlessly. For that reason, the key question of the video now arises: if visibility and color help prevent incidents, who are the people who ensure every day that an airplane is truly prepared to operate safely? When we talk about aviation safety, we usually think of technology, redundant systems, and advanced materials. But the reality is that behind every safe flight, there are people whose judgment, criteria, and experience determine whether an airplane is truly ready to operate. And it is here where the color white, which we have already seen as a tool of protection and visibility, becomes a direct ally of those who work just a few meters from the fuselage. Because at the end of the day, safety does not depend solely on the airplane, but on those who inspect it every day with millimetric precision. Aeronautical mechanics are the first guardians of the integrity of the fuselage. They are the ones who walk around the airplane when it is still cold, silent, and apparently intact. Their training allows them to interpret what the fuselage shows them: a stain, an irregular shadow, a line that should not be there. For these professionals, white is not a decorative color. It is a workspace where any anomalous detail stands out more clearly. And in an industry where critical signs can be minuscule, that contrast makes the difference between a safe flight and an incident. Alongside them work maintenance technicians specialized in systems, composite materials, and structures. These professionals examine panels, joints, fasteners, and external surfaces using not only tools, but also their own judgment. An area where the paint has aged irregularly may be the first sign of incipient corrosion, just as a rivet with a slightly different halo may reveal material fatigue. Sometimes a minimal stain, almost invisible to a passenger, is enough to stop the aircraft dispatch process until its origin is determined. And all of this is much easier to identify when the fuselage acts as a light surface that does not conceal imperfections. Beyond technical inspections, ramp operators are also involved in daily operations, working alongside the aircraft on the apron. They are the ones who position equipment, coordinate refueling, place the stairs, and supervise the safety zone to prevent collisions with vehicles or service equipment. For them, the visibility of the fuselage is essential. At night, in the rain, or on congested ramps, a white airplane reflects lighting better and allows these workers to act with precision and speed. A light surface also makes it easier for these operators to detect marks caused by minor impacts or accidental scrapes, signs that must be reported immediately. All this groundwork does not happen by chance. It is supported by rigorous training, since aeronautical mechanics and technicians must pass strict certifications, accumulate hours of experience, and constantly stay up to date. Their signatures on a document are not mere administrative formalities. They are legal and professional commitments affirming that an airplane is fit to fly. The responsibility they assume is enormous, and each inspection is one more link in a chain of safety that can never be broken. There are everyday and silent stories that show the value of this human work, such as that of a technician who detects a minimal leak thanks to the contrast of the white fuselage, or that of an operator who notices a dent in a fairing after the impact of ramp equipment. There is also the mechanic who decides to inspect an area because the paint seemed to have aged unusually. Small details that, taken together, prevent major problems and allow an airplane to take off with complete safety. They are discrete actions, almost invisible to passengers, but absolutely crucial to aviation. White, then, is not only a technical choice, it is a visual language that facilitates the work of all these people. A bridge between engineering and those who interpret it every day. Thanks to that color, mechanics, technicians, and operators can work with greater clarity, anticipation, and efficiency. It is precisely this combination of technology and human factor that sustains the safety we tend to take for granted every time we board an airplane. Now that we have reached the end of this journey, it is easy to understand that the white we see on most airplanes is neither an aesthetic decision nor an unfounded tradition. Throughout this video, we have discovered that this color, so common that it often goes unnoticed, contains technical, operational, and human reasons that work together to make each flight safer, more efficient, and easier to maintain. From heat management and material protection to damage detection, weight savings, ramp visibility, and the work of the professionals who inspect every detail, everything converges at the same point. White is a choice designed to function. Understanding this completely changes the way we look at an airplane, because that light-colored fuselage, which at first glance seems like a simple canvas for an airline's livery, is in reality a final layer of applied engineering, one more component of the system, as important as a valve, a sensor, or a structural panel. White reduces degradation, facilitates inspections, improves ground safety, and contributes to making every operation more predictable. It is not just any color. It is a tool that helps the airplane maintain its performance and integrity throughout thousands of flight hours. We have also seen that behind all these technical advantages, there are people who depend on that clarity to work with precision. Mechanics, technicians, and operators who interpret every sign, every mark, and every texture on the fuselage. They are the ones who transform that visibility and contrast into decisions that guarantee daily safety. And in that sense, white not only protects the airplane, it also protects human work, making each inspection faster, more effective, and more reliable. In the end, what seems like a matter of aeronautical aesthetics is revealed as a solution perfectly integrated between physics, maintenance, durability, and the human factor. White is, in essence, the synthesis of a philosophy, making every component, however simple it may seem, contribute to safety and efficiency. If you enjoyed this journey into the logic of aeronautical engineering and want to continue discovering how the machines that move the world really work, subscribe and join us in the upcoming videos, where we will continue exploring the secrets that make it possible for these technological marvels to fly every day.